our first technique. So is it on standard?
Yeah.
That's the key word we're looking for.
Yep.
We're gonna, a very, very specific type of problem. Now this is the second one, because technically the separable was our first. So today what we're doing is what are called first order linear. DEs. First order linear. So you just turn in a quiz. So what does the first order part say to you?
It's our first derivative.
Only first derivative. That's the highest derivative, so there's no second. We do a lot of stuff with second. So first order, and it's linear. So the form is going to be something like this. dy dx plus p of x y, okay? Now, what I have on the other side, it's not necessarily going to be 0. It can be anything. So we'll just call it f of x. Not another y, though. Now, most problems don't start off looking like this, but if I manipulate it, I might be able to make it look like this. Now, last day, if this was a 0 on the right side, if that was a 0 on the right side, is this separable?
No.
Well, that's a 0.
Wait, yes, it is.
Oh, well, yeah. Now my function of x and function of y are connected through multiplication. That would be separable, which would be the simplest route. But so let's assume that's not a 0. So even if I throw this over, now I'm connected through addition, so it's not. Okay? So first order linear is if it looks like this. Now most problems are not going to start looking like this. I might have something in front of the p of x, so I just get rid of it, divide through. If ultimately I can get to look like this, this is my starting point. So what we're going to be looking for is something called an integrating factor. There are several types of problems that we're going to look at over the next few days that may have an integrating factor. An integrating factor is going to be a function that I'm going to multiply both sides of this equation by to make it into something that is way, 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 way easier. Now I want you to think product rule for a moment. Okay? Let's remind ourselves. I just did integration by parts today in Calc 2. Now this is not a trick question. When I write this, okay, let's assume u and v do not represent scalars, they represent functions, okay? If they represent scalars, then the answer is 0. It's not an interesting problem. Tell me about u and v. Based on this statement here, can anybody tell me about u and v? Because I go over this in Calc 1 even.
U times derivative of v.
Oh no, not the answer, not the answer. You're giving me the answer. Tell me about u and v themselves.
They're functions of x.
Beautiful. They're both functions of x. Because if they were not functions of x, but functions of another variable, then these couldn't be ordinary derivatives, could they? Mm-hmm. And if they were ordinary derivatives, then your answer would be 0. So that would be kind of boring. So we don't usually write u of x, v of x. You say, well, why don't we? How many of you ever write y of x when you're doing a problem? Nobody does. It's implied that it's a function of x by the nature of the problem. U and v are functions of x simply because they can't be functions of any other variable. This notation tells me there's exactly one independent variable. This is notation out of convenience, but I started today's class with u of x, v of x, and then I showed that we're never going to write it that way. We're going to write uv because we're lazy. Parentheses, variable parentheses twice. I mean, that's so much extra work. We don't do it. So what is this? When I do this, it's u dv dx plus v du dx. I know that. That's product rule. Now, we worked backwards to get integration by parts. That's not our goal. My goal is to figure out something that I could multiply both sides by to where the left side is the result of a product rule. Now that seems like completely whacked at first. Okay, so let's suppose there is a mu of x. Let's suppose there actually is a function out there, that mu of x exists that will allow me to do this. I'll give you a hint. If it's first order linear, there will always be. Mu of x is going to be my integrating factor. Mu of x will not be a constant. Because if mu of x was only a constant, that means that this thing was pretty darn easy. It means that this was not a function, it was a constant, and you didn't need to do anything clever. So here's what I'm going to do. I'm going to multiply both sides by mu of x first. So I have mu of x. And by the way, you could just write mu as long as we understand it's function of x again. Plus p of x mu of x, y equals mu of x, f of x. I am the least concerned with the right-hand side. The right-hand side is what it is. At some point, I'm going to have to integrate it. I'm not worried about it. It's the left side. I need the left side to be the result of the product rule.
It turns out that I think almost every time the d over dx, you can take mu of x times p of x, and that's just going to be your product rule.
Well, look at the left side, though.
Yeah, so,
Doesn't the left side kind of look like first times derivative of second?
yeah.
So just the left side only. I'm going to be lazy and write this. Remember, it's implied that mu is a function of x. So if I do this, what are we going to get? Aren't we going to get mu dy dx plus y d mu dx? Whoops, sorry. I'm writing this wrong. Sorry. D. Okay, stare at that for a moment. Do you all agree that the derivative of this is this? Well, isn't that the first term?
Yeah.
So what I need to do is equate this with this. Well, they both have a y. So this really comes down to what?
d mu dx p of x
It comes down to d mu dx equals what?
p of x times mu of x.
P of x times mu of x. I don't know what mu is. I'm trying to discover what mu is. I know what p is. That's the equation that I'm given. I'm finding mu. I'm given p. Huh. How do I solve this one?
Oh, it's separable, right?
It's separable. So how if I write it like this? 1 over mu d mu equals p dx. I'm going to be lazy. It's p of x, mu of x. We know that. You with me so far?
Actually, where'd you get that statement from that d mu over dx is equal to those two functions?
Oh. I'm multiplying both sides by a mu. I say my goal is that this is the result of a product rule.
Oh, so you're just saying.
Very specifically, what product rule? This one. The derivative of mu times y, because y. How come? First times derivative of second, sitting right there. Oh, so plus second times derivative of first must be this part. Well, I already have the y accounted for. So the d mu dx part must equal p times mu. Does everybody follow? I'm just filling in the blanks there. Haven't actually done anything yet. I don't know what the answer is, but I know the answer is going to come right from here. And you're right, this is separable. I'm not worried about the right-hand side. I may or may not be able to integrate that. I'm not worried. It's the left side. 1 over mu d mu. What's the antiderivative of that?
The absolute value.
Log. Now, don't worry about the absolute value right now because we're going to do this in such a way that we can integrate it. So yes, technically it's that. And the right-hand side, I'll just leave it like this. I said we're trying to find mu. So how do I find mu?
Exponential.
Just exponentiate both sides. I'm running out of room here. Can I say then that mu is e to the integral of p of x dx? What do you think? Folks, that's our integrating factor. One of the most important steps in all of this entire semester is finding that guy. And in general, it's not going to be very taxing. You do not have to do this again. You fast forwarded to that. So if I have a statement of this form, so now let's see if that actually works, okay? I'm going to multiply both sides of this by e to the integral of p of x dx, whatever goofy thing that looks like. So now I have e to the integral of p of x dx. That's some function of x, agreed? Times dy dx plus e to the integral of p of x dx, p of x y equals e to the integral of p of x dx times f of x. Right. So what do I do on the left side? On the left side, I'm going to write the left side as this. Because that's what the left side is. In order to undo that, I'm going to have to integrate the right side. So here's where it comes down to it. If this were absolutely hideous and gnarly, I might not be able to carry this out. It's not that hard to make up a problem where the thing you're integrating is just, it's beyond us. The tendency is though, that'll be rare in the books because you can't do anything if you can't integrate this. So the problems are generally, I don't want to say dumbed down, no, wrong word, reverse engineered. So that you can actually proceed to the end, because I like people to be able to get to the end. Calc 1, the last lecture in my Calc 1 class, we do arc length and surface area, right, things by rotation. And the instruction in every calculus book ever written is set up the integral to find the arc length, or set up the integral to find the surface area. Not find the arc length or surface area. Why? Because there's only 3 problems that exist that you can actually find the arc length of. Only 3. That's it. Of the infinitely many things, only 3. And I do all 3 of them in my Calc 1 class. There's about 6 that you can find the surface area of. So all you can do is set up the integral, and then you wave at it as you walk away. Then in Calc 2, you learn how to do this from a parametric standpoint. You can add very many more, and then in Calc 3, you do even more. But in general, you have integrals that you can't integrate, so there's really no practice. So I try to do problems that you actually can go to the end of the problem so you can get something out of it. But as long as I can state the correct integral, that's a starting point. And we were doing some of that last day. We were stating the correct differential equation. We may or may not be able to complete it right now. But if it's possible to complete, we will. So let's do some problems and see how this works. You're going to like this because it's very clean. The hardest part is not going to be solving the problem. The hardest part is, as you're learning techniques, is to look at a problem and categorize it. Which technique does this fall under? When you, back in Calc 1, when you're first learning integration, right? Wasn't that the trick? Looking at an integral and say, what kind of integral is this? And I don't know if I did this on the first day of this. I know I did this on the first day of Calc 2. You know, you're in my Calc 1 class. I'm notorious for putting these problems back to back on that integral test at the end.
The one on the right is just the direct integration because the top is going to be the derivative.
So
like, you
do
can-
these problems at first glance basically look like the same thing? First glance?
The right one's possible, the left one's like.
Well, no, they're both possible, but they're both very different.
Yeah.
The one on the right is a straight up simple u sub. And you remember, if the degree of the numerator is exactly 1 less, then there's a really good chance that the numerator might be the derivative of the denominator. So the one on the right is a simple natural log 1 step.
The one on the left, some arc tangent probably.
Close, inverse.
Yeah. Oh yes, inverse.
So that's inverse tan.
Yeah.
The point being, you cannot do either one of these unless you could categorize it. Oh, that one looks like the derivative's on top. Okay, that's going to be a log. Oh, that one looks like a sum of squares on the bottom. Blah, blah, blah. That's what you had to do in Calc 1 in order to be able to answer the question. Then in Calc 2, you're looking at problems and they sometimes don't look a whole lot different, and you're saying, oh, that looks like an integration by parts. Oh, that looks like a trig sub. That looks like a partial fractions decomposition, right? We talked about this. The moment you could classify the problem, then you had a strategy to finish it. But if you couldn't classify it, you can't start it. You know where to go. So our first thing is it separable? If it is, do it, because that's going to be the fastest. The second thing is going to be, okay, if it's not separable, is it first order linear? That's literally going to be the second thing we do. So let's do a problem. Let me just grab one randomly. I'm not very good at just making them up anymore. I'm operating on the old software. I used to just make them up at random, and you know what it turns out always happens when I just make them up at random? People snicker because it's like exactly the problem I have on the quiz that I wrote a month ago, and I'm making it up at random, and I often make up big. Have I ever done that, Benito? I do exactly the same problem, and I don't even realize that people will be laughing. Well, thank you. Okay, let's do one. Okay, this is not too terrible, I hope. Let's see. X squared minus 1 dy dx plus 2y equals x plus 1 quantity squared. Okay, is this first order linear?
Yeah.
Well, the first order part is easy enough. The y or the dy dx, are either one of them involved in a function? Do you see exponents? Do you see? No.
No.
So it is first order linear. Is it in the form that I can find the integrating factor?
Yeah.
You have to divide the x squared minus.
I got to do something first. So All right, is it now in the form I can work at? Before I go any further, that quantity on the right's kind of intimidating, isn't it?
Don't we have to
Do we have to divide the two y?
Did I?
by the
Oh,
x squared?
thank you, yes, sorry. Standing too close to the board. Yeah, that is kind of important. Okay, good. And that would be y. Make sure, okay. Ooh, good catch, that would have not ended well. Can I do anything with that quantity?
Not really.
You
Which
can
is
simplify the
On the right side?
On the right side, yeah,
can
it's,
cancel.
Oh, you can
it's
do
a
x
sum
plus
of
one.
square, product of.
Difference of squares. You're almost
Yeah,
there.
yeah.
The bottom's a difference of squares, the bottom's x plus one, x minus one, so can I cancel something?
Yes.
Yeah, tell me a better version of this.
X plus one over x minus one.
Yeah, that's immediately better, do you agree?
Okay.
Now, I can still manipulate that, I can do longer synthetic, but I'm gonna hold off because I don't know what my integrating factor is gonna do yet.
Cause you know how you wrote it in that form, like, the dy dx plus px mu x.
But I've got it all erased.
Is the px in this case the two divided by x squared minus one?
Yes, hold that thought for a second, because that's it, that has everything to do with my strategy. Do you notice that how I wrote it? I wrote it as something times y.
Yeah.
I don't have y in the quotient, that just is confusing. I have a function of x times y.
I think
That
we
is
have
most
to
definitely my p of
trace
x.
cell to solve that.
I think I did this correctly.
Don't we
Yeah.
have to like substitute the x with the sine, or secant or something, or tan?
Now,
Trace cell to
unfortunately, this one's not gonna be very friendly. Let me make sure I did that. Yeah, I wrote it down correctly. We'll do this one off to the side. It's not the answer that I'm concerned with as much as being able to generate the integrating factor. So, our integrating factor is e to the integral of
Actually, no, that's just part
2 over x squared minus 1 dx. We don't love that one. Now, there's two ways we can do this one. Okay, now it's not on your sheet, unfortunately. This is Calc 2. There's two ways I can do this. And by the way, does anybody actually have a textbook with them? This is on the cover of every book.
Secant.
It's,
No,
no, isn't it a hyperbolic?
no. You're either gonna do a partial fractions decomposition or a trig. So partial fractions is always faster.
Yes.
So you have,
X equals secant.
you have a formula. You have a formula for things of this nature. I'll write it like this. 1 over x squared minus a squared. Now, I don't know off the top of my head, but this is gonna be x plus a, x minus a. So that means you're gonna do, remember doing stuff like that?
Yeah.
So then what's gonna go up here? I think this is going to be a -1, and that's gonna be a +1, and I think we're gonna have a 1. Is that right? Let's see. Or no, 1 over a. I'm just doing this real quickly. So that's gonna be -x plus a, +x plus a.
Oh, and it cancels out then. with that.
So then what does this give us? This gives us 1 over 2a times what?
Natural log.
Log x minus a over x plus a, using fact.
Yeah.
Okay. Is that good? That's really good, because I have an e. What you find is it is often the case that that horrible integral is going to be a logarithm, which is actually your favorite thing because it's e to the. So right now, what do I'm telling you, this is the antiderivative right here.
Mhm.
What is my a in this case?
1.
1. Ooh. Now, by the way, I am not worried about your ability to do this guy. I grabbed one that was particularly ugly looking. I'm walking you through that part. I doubt anybody remembers even how to do those. You remember that you did those. And you're not going to do very many of those in this class. That's not the problem. So what is my antiderivative then?
1 over 2 times 2. So
But I
that's
have that
1.
guy.
Yeah.
So isn't it just going to be log x minus a over x plus a when all's said and done?
Yeah. And a is 1.
So far so good? Now, what am I leaving out? Isn't there a plus c?
The 1 over 2a thing?
Yeah.
Well, no, because the a is 1.
So
Yeah,
this is
that's
like,
true.
there's a
So it's
square.
1 over 2,
Just like,
but I have that 2, so it cancels.
That's true.
oh, is that?
C, and then the C will come down from as a.
Okay, so hold this thought.
Oh, times C, because when you,
Well, hold the thought a second. Shouldn't there be a plus C here?
yes.
Alright.
We don't really need to worry about that, right?
You're right, but do you know why? I'm gonna explain to you. I just went over this, I reminded people in Calc 2 the other day. Calc 1, you're doing a definite integral. And just let's keep it real simple. I want to integrate, I'm not gonna tell you, I don't tell people things, we figure it out, we find everything out. Because if I tell you stuff, you memorize stuff without any basis. What is the answer to this? It's x squared plus c, okay? Now I want to do this problem from, I don't know, from 2 to 5. So now the answer is x squared plus c from 2 to 5. Okay, I'm going to be really strict. So then it's 5 squared plus c minus 2 squared plus c, which is just 5 squared minus 2 squared. Am I going to get the same answer no matter what the value of c is?
Yeah.
Yeah, your Calc 1 teacher may not have told you this, but this is absolute. The reason you never wrote the plus c in a definite integral was not because you can just drop it, pretend like it's not there. It's first that every value of c is always going to give you the same final answer. Therefore, if every value of c gives you the same final answer, you actually get to choose the value of c. And you will always choose c to be 0. Guess what? In the integrating factor, this is the only other place mathematically you'll ever see this. Every value of c is going to, in the end, give us the same integrating factor. Every value of c will give us the same integrating factor. I'm going to prove it to you. Plus c. So won't that be e to the log x minus a, x plus a, times e to the c? So let's just call that, I don't know, how about k? You with me so far?
Mm-hmm.
Now I have an e to the log. And now this is just k, x minus a, x plus a. Beautiful. So what am I going to do with this? I'm going to go back to this problem here and multiply both sides by the integrating factor. And every single term on both sides of the equation is going to have a k in it. And what are you going to do first? Cancel the k's. Which means every real number of c gives you the same final result. It's not in the final answer. So you are going to choose c to be 0 every time, so you don't have to worry about it. This is the only other area you get to do this. Not because, oh, we're just going to ignore it. No, because every value of c is going to produce a different e to the c. So there's an infinite number of possible, I called it k. But because it shows up on both sides of the equation, you're going to cancel it anyway. You like that one? You should. So in the integrating factor, you don't have to worry about the c.
It was confusing at first, but I was like, wait a minute, you could just.
It's
it
always going to
cancels
cancel.
out.
It's
So,
always going to cancel.
why would you deal with it?
But if someone just said, don't worry about the c, you'd say, but wait a minute, won't different values of c give me a different integrating factor? It'll give you a different integrating factor, but it will not give you a different result to the final problem. There are an infinite number of integrating factors, and guess what? They all differ by a constant multiple. And since the constant multiple is going to show up on both sides of the equation, it doesn't matter what that constant is. That might as well be a 1. So now let's go back to here. I like stuff like that because I'm inherently lazy. It just makes my life easier. So I'm going to multiply both sides by, where is it? There, I wrote it somewhere. Oh, it's actually it's x minus 1, x plus 1. Sorry, I forgot that's what it was. So I'm going to multiply both sides by x minus 1 over x plus 1. What's going to happen here when I do that?
Yep.
Something's going to cancel,
Yeah,
isn't it?
that's minus 1.
I think that's going to end up being x plus 1
Yeah.
squared now.
Yes.
Does that look right?
Yeah.
Because I think we just did this. And I'm multiplying by, oh my gosh. Well, I'd say this is what we refer to as serendipitous. This is a proper use of the term. Good fortune. Everybody got that? My integrating factor was exactly the reciprocal of this. That's just coincidence. Now, whoever organized the problem kind of figured that one out. Now, here's the part that I need you all to do or not do well. Okay, I'm going to erase this because we now know what the integrating factor is. Okay, what is the left side? The left side is d dx of the integrating factor mu, which in this case was x minus 1 over x plus 1 times y. Do you agree?
Yes.
First times derivative, second times the derivative of the first. Now, if you're not sure, go ahead and differentiate this. It's a straight up quotient rule. So you already know the bottom is going to be x minus 1 quantity squared. And the top's going to be, right, bottom times the derivative of the top, that's 1, minus top times the derivative of the bottom, and so on. Okay? And that's going to be 2. And then you get back to here. What's on the right side? So far, so good? How do I write the next step? And by the way, I just checked it. Always check. First times derivative of second, okay. Second times derivative of first, I might have to do a little bit of work, but yes. Okay. Do not write an integral on the left side. It's very confusing notation. You can't have an integral with x and y in it. Don't write this. I have a lot of people who will do this. And now I'm going to integrate this. Really? How are you going to do that?
You have to integrate the derivative.
Yeah, but you have an x and a y. Don't do this. Never do this. No, check out what I'm going to do. I'm going to integrate the left side. I'm done.
Yeah.
No matter how many times I say it, you're done. You just integrated the left side. Why would you do anything other than the integrate? No, I just integrated the left side, didn't I?
Yeah.
But I still have to integrate the right side.
And then X.
This is how things should always look. When I figure out the integrating factor, I'm going to write it in this form, mu y, and actually check it, because what if you made a boo-boo? There are a million places where you can make trivial errors, but it'll completely change the nature of the problem. I'm not going to make errors, but I'm going to point out as we do problems. You know, if we make an error here, it'll change everything. So I always check it right now and see, did I get that? Now, what do I have on the right side?
X plus C.
And that C, I don't get to pick 0. For me to find the value of that C, what would I need?
Initial condition.
I need an initial condition, and it's very unlikely that that C is going to be a 0. I'm not worried about that. Okay? I want to write y equals. Are they done next time?
I think so.
Could I trouble you, just look on the desk, see if you can see that pin. It'd take 2 seconds. It's either right and visible, right in clear view, or not. No, because there might be another class coming in before we're done, and I won't be able to do that. I don't really want to wait till tomorrow to know if I've lost it or not. Now what?
I think that's good.
Yeah. We don't know the value of C. Just wave at it as you walk away. Oh my God. Benito, that's easily 100 miles.
Wow.
Yeah. We won't worry about it because that seems to be working. You guys did a great job of jerry rigging that, but I hate to say it, I'm really glad I have this back now.
Yeah.
So for that term on this side, x
Which
minus
that
1,
term?
x plus 1 dy dx. And then you're setting that term equal to
Okay,
1.
back up a second. I figured out what mu was.
Right.
So I just multiplied everything by mu.
Yeah.
Boom. Now, if I did it right, this has to be d dx of mu y. That's what it has to be if I did it right.
Okay.
If I did it right. That was the whole point. Now, whether you write this or whether you write this, okay, mu derivative of second derivative of mu. Now, sometimes that's so easy you can do it in your head because it might be an e to the x, or it might be something really simple. In this case, this was a little bit more work. We can live with that. And once I have that, then the next step is to just undo it. Now, the work is not going to be usually finding the integrating factor. The work is going to be doing the manipulation all the way through. No part of the problem in general is going to stump you, but there are a lot of details that if I'm not really on top of things, I can make mistakes. Okay, and it's very easy. For example, if you ask me off the top of my head, what's the antiderivative of this? I don't know. I don't bother memorizing antiderivatives. I have a hard enough time with phone numbers. No, I just figured it out. I showed you guys how you did it in Calc 2, except I did it a little bit faster. Because I just fast forwarded to the end. But is it the x plus 1 on top or the x minus 1 on top? I don't know. We just did it. So we figured it out. So this one here this is probably more work than most, although I think the ones that give people the most trouble are probably the ones involving trig. So let's do one of those. All right, let's do, hopefully I didn't ask this one on a quiz, I probably did. All right, cos squared x sine x dy dx plus cos cubed x times y equals 1. Well, is it first order linear?
Yeah.
Yeah.
It's a redundant question because you'll say, well, it's from that section, so the answer is yes. But if this was an exam where I have problems from all over the place, the answer could be no. So you still want to get in the habit, look at it, and answer the question as soon as you possibly can. Do not labor over it. It doesn't require explanation. I only have two things involving a y, and they're both linear. Well, you know, they're good. Okay, so what am I going to do first?
So isolate dy.
Cosine.
Yeah, basically get dy dx without any coefficient. So go slow. Cosine squared, okay, I'm going to cancel some stuff.
Yeah.
But be really careful. What am I going to get as a result? And off to the side, you know, I'll write it out off to the side because I do not want to mess this up.
Yeah. Yeah, it's a cotangent.
Cotangent, good. I cannot afford to make a mistake there. If that's not correct, then I'm going to have the wrong integrating factor. Then, you know, all hell breaks loose. You guys are going to get so used to seeing it, you know, and it'll go way beyond dog sleeping with cats at some point. You know, that's just how it starts. So this is cotan x times y, and over there here I got a bunch of stuff. Now, do I want to write it this way, or do I want to write it? Generally speaking, you never write the reciprocal of a trig function because the reciprocal of every trig function is just another trig function. So because I've got to manipulate later, if I believe that I'm going to get a whole bunch of canceling later, is there anything wrong with me writing this way for right now? I'm not going to integrate this. I'm going to integrate this times the integrating factor. But maybe the integrating factor cancels everything. Or maybe I just don't like the form of that, so I'll write it as secant squared cosecant. For right now, it truly doesn't matter. What does matter is that is absolutely correct. Now, cotangent's antiderivative. I wouldn't say that's in the top 5. I don't even think that's in the top 10, but it is actually not a complicated one. It does not need technique, and I will remind you.
The derivative is on the top.
Yeah.
So it's just ln sine x.
This is why you know this one, because it's already. This was one of the simpler ones to derive, cosine over sine. It's the derivative on top, so it's just log of sine. Everybody cool with that? That's off to the side. Okay, so now I'm calculating my integrating factor. Mu is e to the integral of cotan x dx. I like this one.
Ooh.
This one's
Ooh,
cool. It's just sine x.
It's just sine x.
So when we do the u sub, does it make it?
No, you don't have to do u sub. I did this in case you didn't remember.
Yeah.
The antiderivative of cotangent is on the list of 20. It is the log of the absolute value of the sine. But if I forgot,
Yeah.
that's how we derived it in Calc 1. You go, oh, yeah, that's right. That was not a complicated derivation. That one was actually pretty friendly.
These absolute values seem to be kind of messing me up a lot of places. How do we get rid of the
No,
absolute value?
you're not getting rid of the absolute value. It's when you exponentiate, you're saying, okay, how does that change things? It changes things. One of the questions, this is an important question. We can't just pretend like it's not there. One of the questions on the quiz you just turned in, it said, assume an appropriate interval of solution. In the end, do you think my solution is going to be true for all values of x?
Maybe not.
Maybe or maybe not. I got to see, because will there be values of x that don't make this work? Well, actually, as it turns out, when I do my integrating factor, it isn't going to change things at all. When I exponentiate, it's going to be, I can leave this like as the absolute value of sine, because I'm going to be doing e to the log, and that thing's got to be strictly positive at some point. But when I'm multiplying both sides, then I go back and say, will this have changed my answer at all if I do this? So for the purposes of integrating factor, the absolute value is not going to get in the way. You've done this before when you did inverse trig way back then. I won't go into it, but in Calc 1, when you were doing things involving restricting the domain and you were working backwards and finding things, sometimes there would be an absolute value involved, and sometimes you say, you know, it didn't make any difference. It didn't change my answer. Okay? So we're going to go with this. Now, when I multiply both sides by this, I'm going to be glad I left it like this. I need a different color now. That one's going to run its course. I'm going to multiply both sides of this equation by the sine function. Now be very careful when you do that. So I'm going to get sine x dy dx.
That's pretty cool.
Plus what?
Plus cosine of x.
Now, I say this in all seriousness, and a lot of you, like I said, you've been in my classes before, so you know this. And I want to remind you, because this is critical information, really in math and physics. You guys remember the 3 rules of life? And so some of you, it's been a while. Remember, the first rule is chew all your food before swallowing. Second one is keep all your limbs in the car while it's moving. And the third one, of course, remember, don't forget to breathe. But I always remind people in calculus there is a 4th rule of life. And remember, if all else fails, guys, fill it in for me. Change everything
Back to sine and cosine.
to sine and cosine. So you've learned the rules of life. That's the 4th rule a lot of people forget. If all else fails, change everything to sines and cosines. I'm out in the middle of the desert, there's no water, just change everything to sines and cosines. An oasis will appear. I'm looking at this, I don't know what to do. Change this to sines and cosines. Change this to sines and cosines, and everything just falls in your lap. You're looking at things thinking you need to have memorized identities. Well, what's cotangent times? No, change it to cosine over sine. Oh, now cosine over sine times sine is simply
Cosine.
cosine. And then the right side is what?
Secant squared.
Just secant squared, because cosecant is 1 over sine. Do not write cosecant times sine in your final answer. They cancel. Now, I'm staring at that going, okay, if I walked in the room right now and I saw that, I wouldn't know what to do with it. But because of the nature of the problem, we did the integrating factor, we multiplied. Now I know exactly what to do. The left side must be the product rule applied to what?
Sine x times y.
Of sine x times y. Because sine x was my mu. Now I check it. Most people just keep going at this point. We didn't make a mistake. But if we had made a mistake, our final answer would be incorrect. We'd never find it. So the check I do right now is actually, most of the time, it's going to be trivial. First times derivative of second, okay. Second times derivative of first, okay, is perfect. It's usually that easy. But the problem is going to be, based on the nature of problems, sometimes this is going to end up being a minus sign in front of here. There's things that are going to happen where you're going to say, hey, that's not working. Oh, it's because I made a mistake in finding my integrating factor. Maybe I had a reciprocal. Something goofy went on. I'm feeling pretty good about this. There's nothing to do on the right side yet. Drum roll, please. I'm integrating both sides.
Tangent x.
Could I just do that? Is that legal?
Yeah.
I said it out loud. I'm integrating both sides. Oh,
Yeah.
well, that wasn't that bad, was it? Change everything to sines and cosines.
So secant x plus c over sine of x?
C.
Can you do better?
Cosecant
Oh yeah, that's even.
x.
CC.
C.
Yeah, maybe we put C1, I don't know. Not divided by sine times cosine. Was that terrible?
No.
No, but was it scary at first when you saw the problem? Oh God, trick stuff. But that's kind of the nature of what things look like. You will get very, very fast at this, but this is why you have the sheet of integration in front of you at every class. Because to find your integrating factor, you're always going to be integrating something that has some familiarity. Often it'll be easy. It was easy in this problem. It wasn't easy in the last problem. It won't always be easy, but I guarantee you every problem that you're asked will be one that you actually can navigate to the end. Otherwise, it's just not a good question in the textbook. It's not that question doesn't exist, it's just we're not practicing those ones.
No.
Question,
You
sorry.
can always parameterize the exponent.
Parameterize?
The exponent? For like the impossible integrals.
Oh. No, we're not gonna. One thing about DiffyQ, it's like Calc 1. I can make a money back guarantee. Every integration problem any Calc 1 student has ever run across in the history of Calc 1 was always something you could find. You never had problems that you couldn't integrate Calc 1. Is that true in Calc 2?
We had this professor, Marquez, he would give us impossible problems that.
In Calc 1 or Calc 2?
functions.
In Calc 2.
In Calc 2, that's why you learn things like series. You learn Taylor polynomial ways of estimating the integral that had no antiderivative. Calc 2, no, you can't integrate everything, but you learn how to deal with those. But Calc 1, every integral you can pretty much do, otherwise you're just not asked that question. Or it was set up the integral but don't evaluate it, like arc length problems, things like that. So it's almost cheating to say, let's look at the next problem. I wonder if we can do it. Yeah, we can. We can't always do things, but these ones we pretty much can. All right, so, hold on, where are we here? Lost my place. Here we, sorry, I'm trying to find the problem I was looking for. I had notation, but I grabbed a different textbook. Sorry, I have a problem that was picked out, particularly evil. Why am I not seeing it?
Waiting for it.
Oh, here it is. Here it is. Yeah, this is just feels wrong. Sorry, it took me a moment to find the problem.
Whoa.
Is this first order linear?
No, wait, yes,
Yeah.
it
This
is.
is not.
In what variable?
In X.
We're
Reverse.
using
X.
x's as a
Yeah.
function of y.
Can you do that? Can you have dx dy? Sure.
Yeah, sure.
We did. We just
You
did.
just said so.
So if I'm thinking graphically, I'm thinking sideways.
Yeah.
But is there any, change the letters of the alphabet. It doesn't matter. Can I do this one? Yes, I can. And it actually is first order linear, but I'm looking at a different variable now. Automatically, that's tricky. All of you had Calc 3 at some point, and a lot of you had Calc 3 with me. And I always maintain, most textbooks would give you 3 formulas for every type of problem, because are you orienting it this way, or this way? I'd say that's a silly thing to do. I have a situation for you. Maybe I want you to find the surface area of something. Maybe I want you to find the work or something, and I give you the situation. All of you would do the same thing. I'm going to call that the floor. I'm going to call that the ceiling, because it's easier for me to orient things in this direction. It would not have changed anything if I oriented that way to the XZ plane or that way to the YZ plane. But we said, no, let's make the XY plane the floor, because my brain can conceptualize it easier. So we only need to do one problem. We set it up how we wanted to set it up. When you guys are doing a simple integral, even in Calc 1, do you tend to go vertical rectangles or horizontal if it doesn't matter? Everybody does vertical, because that's it's easier for your brain to conceptualize, but it wouldn't change anything. So it never matters which one's the independent variable. I just have to recognize it and set up the problem that way.
Just a quick question. Now, if we had x as the dependent variable here, would we usually see x of 1 for the initial?
Yeah, that's why it's kind of tricky.
Tricky.
Can I treat this as x of 5 equals 1?
Yeah.
Mhm.
Right now, what is the value of x?
1.
1, and what's the value of y?
5.
5.
Oh.
So you could actually,
Yeah.
there'd be an easier way for me to interpret this. It passes through the point 1 comma 5. That's actually saying the exact same thing. So does it matter if I say it this way? Does it matter if I say it this way?
No, but
No.
it's easier.
This is thrown in there just to confuse, but it doesn't change anything. These 3 say the same thing, because I'm taking a point on the curve to give me the specific value at the end. Because there will still be an arbitrary constant, but only at the end of the problem, not during. Okay, so how do I start this, folks? Help me out here. Walk me through.
Divide by
Isolate.
y.
Yeah.
So what am I getting rid of? Well, I'm getting rid of that y. So this now becomes dx dy, dx dy. Now, how do you want to write this?
1 over y.
Minus 1 over y times x.
1 over 2y. Oh, 2y squared. Times.
2y.
Oh, wait, 2y, yeah.
There are like 8 different versions. 2y. How about just 2y? Yeah, I like that one. Because. Oh, or you mean the variable? No. Okay. Are we good?
Yes.
So, this is the problem we're going to make mistakes on, not because we switched x and y. No, this is the problem people make mistakes on because of this minus sign right here. This is the most missed type of problem of this nature, and you'll see why in a moment.
Yeah, because.
So my integrating factor is e to the integral of negative 1 over y dy.
That's negative ln of y, but then you have to put.
Which is just y, right?
Yeah.
No, no, it's not.
I'm winking with my left eye, you know what that means,
Yeah,
right?
it's 1 over
You
y.
know something's up. No, it's not y. What is it?
You gotta put
So
the
y to the negative, it's y to the negative 1, right?
It's e to the log of y to the negative first power. The exponent comes up, but this is 1 over y.
That's so weird.
That is the universal error. We ignore that negative sign, and so we all say it's going to be y as opposed to 1 over y. If there were a constant here, we would end up seeing that constant as an exponent. That's not a big deal. But where this one, the y should end up in the denominator, a lot of times we're going to have it end up in the numerator. And that negative sign is why it was so important. So I said earlier, most of the mistakes are made because of the sign right here in the beginning of the problem. And by the way, this is another reason we are going to check our answer when we check our answer, so we ensure there's no possibility we have an error. So let me go this way. I'm all over the board today.
I mean, even just a positive constant, we still have to put that up to the
I'm sorry,
top.
say again?
Even just like if it was a positive constant, we still have to put that up to the top.
Yeah, because I can't exponentiate with any coefficient here.
Yeah.
It wouldn't matter what's there. That has to come up because it's e to the log, not e to the something log.
That was
So-
really confusing for me.
I'm going to multiply both sides by 1 over y at this point. And I'm multiplying both sides of this by 1 over y, by the way. So now I have 1 over y, 1 over y, dx dy, which is already confusing, minus 1 over y squared times x equals 2. If I did it right, this should be the derivative of 1 over y times x. And I'm differentiating, whoops, sorry, that should be dy. So, first times derivative of second, is that what that is?
Yes.
Second times derivative of first. The derivative of y to the negative first is negative y to the negative second, which is exactly what I have here. This is why you have to check it right here. The plus or minus, ignoring it, making a mistake, is probably the most common error. If I incorrectly, let's say I really messed this up and I had y, okay? Then when I got to here, I would have y times dx dy, and everything would look fine, except the problem is the subtraction wouldn't show up in my product rule. And I'd say, hey, wait a minute, these terms are being added and I have a subtraction, what's going on? Well, that's what's going on. But now this is plus negative 1 over y squared, which is perfect when I check my product rule. So I know this is correct now. So here's my favorite part. I don't have to do any work now. I'm going to write it like this, because a lot of us are going to mess that up because we forgot we're integrating with respect to y, not x. You with me so far? And so what's this? 2y plus c. It doesn't matter, but can I figure out my c right now?
Yes.
Yeah, might as well. I could also multiply both sides by y, and I'd get rid of it over there, but then I've got
Y
2 of them over here, and it's, yeah. So y equals 5, x equals 1. So here's what we have so far. I'll go back to here. I have x over y equals 2y plus c. You agreed? I'm going to go ahead and put the numbers in. You said y equals 5, x equals 1. So 1 over 5 equals 2 times 5 plus c.
Hard math.
So c is what?
Negative 49 over 5.
Negative 49 over 5. And I'm going to leave it like that because we got to manipulate what we have next because we're still moving things around. This thing. So right now I have x over y equals 2y minus 49 over 5. How do I want to write my final answer, by the way?
In terms of y.
Do I want to write x equals or y equals?
X equals.
I actually want to write x equals because we said x is the dependent variable. Oh, let's multiply both sides by y. Then I'd have x equals 2y squared minus 49 over 5y. That's it. I don't need to do anything with that. What is this the graph of?
That's the rumor thing, the epidemic.
49 over 5 is the gravitational acceleration.
If I just said, what does this look like on an xy plane where x is horizontal and y is vertical?
It's a sideways parabola.
It's a sideways parabola. Yeah. Now, does it have any application? It can, depending on what your x and y represented. But if I just said, what does it look like on a xy plane? What if I made x the vertical and y the horizontal?
Then it
Then it'd be an upwards opening parabola. Who would ever make x on the vertical axis? Well, isn't in physics x always the vertical axis? But we make t the horizontal.
Yes.
Does it make any difference in terms of your math? No.
This is so weird.
It's totally weird. It's out of control the way it is. Okay. You guys good so far? Every problem we've done has been different, but they all have the same big picture. Once I recognize that it is first order linear, I can proceed. What would determine what makes a problem difficult? There's two pieces that could make it difficult.
If the integral doesn't work out.
You're probably going to be able to integrate for the p in general, because the p is not going to be something terrible. But it may turn out that your thing ends up being an exponential function.
E to the power. Of something.
Yeah. What if my p is something simple, like my p is x squared? Oh, now it's e to the integral of x squared, so it's e to a function as my integrating factor. And now I'm multiplying both sides by e to the something, which almost guarantees that not the left side, but the right side's going to now require integration by parts. And integration by parts is the most common of the techniques that you learn that you're going to apply, because it will apply in this situation. Let's go back to this problem. What was our integrate? This was not bad. In the previous one where it was sine, what if my right side, instead of being a simple trig function of x, what if my right side actually was x? And now I'm multiplying it by sine. You're going to integrate x sine x, aren't you? That requires parts. It turns out that there's a tremendous number of apparently simple problems that are going to require parts. We're not going to spend time on that. It will come up occasionally. We will not dwell on it. We just know that it is there. Unfortunately, I know somebody who taught this course a couple years back. I think it was, I can't remember if it was right before or right after the pandemic, but it was their first time teaching it, and they were all jazzed and all excited, and they were working problems in class, and they gave the first exam, and I think they gave something like 10 questions, which is kind of a tough exam. I think she told 7 of them required integration by parts.
What?
And the class died, they rebelled, they were, getting ready to, grab your torch and pitchforks, the whole thing. And I said, you gave them a differential equations exam that had, she goes, well, I told them, that's a possible question. I said, she goes, what would you have done? I said, well, your questions were great. First of all, I probably would have made the integration by parts a bonus problem, because you know that none of them remembered how to do it. I said, had you been practicing them then in class? And they said, well, not really all that much. I said, yeah, that may have, it worked out in the long run, but they dug a hole for themselves right off the bat, because they gave a DiffyQ test. They said, literally, class all failed. And they weren't a good class of failing people, but they asked questions that no one was ready for. Integration by parts is always a potential thing, but it's only going to show up in one area of the problem. So now, you already answered the question well. What if I can't integrate it? Okay, what if it is something beyond me? Do you think there's integrations that are beyond you? Yeah. That's really easy to have integrations that are beyond you.
We can estimate them.
How about we do something like this? I'm going to set a really simple problem.
Yeah. Are we allowed to graph and estimate?
I'm going to set up something nice. And, okay. First order linear? Yeah. What's mu?
E to the
integral of x. Oh.
Okay, so now, let's multiply both sides on the left
Okay.
by that. I'm going to walk you through exactly what to do, because if you said, how many times does this come up? Infinitely many. How many times does this come up compared to what we've done? Infinitely many times. I'm going to walk you through exactly what's going on in this problem. Okay, so that's my integrating factor. So I now have e to the 1/4 x to the 4th dy dx plus x cubed e to the 1/4 x to the 4th y equals e to the 1/4 x to the 4th times the secant of x. You up so far? Now, what's the left side? If I did it correctly, what do you think? First times derivative of second, okay. Second derivative of first would be this, and then times the derivative of that. Okay, good. Hey, so far this has been pretty easy.
Yeah. Now we do this thing. Can't we just use series expansion?
Nah, we could, but in this case, it's not going to help us. Why?
Maybe the x
Because we don't
powers
have
of
a. Oh, yeah.
Got that thing. Okay, now what? I'm done. Wave at it as you walk away. Why?
Because I don't want to do that.
Well, it's impossible. There is no technique that exists. There's no technique that will ever exist. And if it's an indefinite integral, we can't even use a computer. That will only help if it's a numerical solution.
Oh, I see.
So we wave at it, we walk away, because that's the answer.
Yeah.
By the way, isn't every answer exactly this? Isn't every answer going to be 1 over mu times the integral of mu times whatever was on the right side, which I call generically f of x? If you look at every problem we've done has this final form. We just were able to integrate that. It is very realistic that you could have integrals that you can't integrate, but can you still tell me what y equals? We just did. Now, someone said, what about things like series and things like that? Up to a point, yes. I threw in the secant just because I'm in a really foul mood right now. If it wasn't for the secant, I probably could use a series, and in fact, in reality, I probably would use the series. But that's so over the top, right? But do you see my point? We still were able to state the final answer. We just couldn't integrate that. What if that is something we should be able to integrate, but we're just blanking out? Have I still said something correct?
Yeah.
I just haven't finished it, but I have no errors. So it's not wrong, it's just not done. There's a big difference. I always remind people, you're working a problem in any class and you get to a point and you're like, should I keep going or should I just leave this alone? You know if an answer can be simplified because it's a better final answer. No one here writes, and the final answer is 8 over 4. You'd probably write 2. You're not wrong, you're just not finished. Being incorrect, this would be like me giving you directions to my house, and it's fairly long directions, and you spilled coffee on it right before you got done, so the very last part, the part that had my street address, you spilled coffee on it. So you end up on my street, and you get out of your car and you start knocking on the doors until you get to my house. Okay. Are you lost? You're on my street. But you didn't quite finish. In other words, you're not wrong, you're just not finished. You didn't quite get to my front door yet because you spilled coffee on the street number. So you're just going to knock on the houses in my neighborhood until you find it. No, you took a left at the stop sign rather than a right out the door. Are you lost?
Yeah.
Oh yeah, you end up in Temecula or some TJ or someplace and go, I can't find Mr. Brown's house. Being incorrect and being unfinished are not even similar concepts. We have nothing wrong, we're just not finished. And in this case, we can't finish. There will be problems that you're supposed to know how to do. Yeah, it's an exam, and you stayed up way too late last night, and about halfway through the exam, your coffee is completely worn off, and you start drooling, and you realize, I have to integrate e to the x. I'm just telling you. I gave a Calc 1 exam last semester, and in their integral test, we started it. The first integrals were the integral of, I think, sine, cosine, x squared, and e to the x. And I say you got to do 3 out of 4. Most people skip the e to the x. I don't know. that was probably the one that you could get right even if you didn't know what you were doing. Yeah. They skipped e to the x, the integral of e to the x. It's just, it was that whole plus c thing really messed with. No, it wasn't that. I don't know. And by the way, they get to bring all of their integral formulas with them. That's probably not one they should have skipped. But we get to a point you can't continue, you do what you can. I'm not showing you backdoor methods, I'm just saying there will be times you can't finish. But here's the thing, when you are in that real job, and you're working on that big project, you're an engineer. How many here are engineering bound? Who is not engineering bound? What do you guys?
Physics.
Physics?
Chemistry.
Chemistry?
Biochemistry.
Biochemistry? Any math? Just math? Okay, you get bonus
I
points.
love math.
I'm
Love math, it's my favorite math. Are you always gonna be doing everything alone? No, you're rarely gonna be solving things alone. You're usually gonna be working with teams. So you got to that point, you don't know what to do, and you have to, he does know what to do. Can that happen? Yes. Those who were in my Calc 3 class, you remember when we talked about changing the order of integration from dy dx to dx dy? And I said, you're given an integral and you're looking at it going, I cannot integrate it. So you had to work backwards, figure out what the region looked like, go from vertical to horizontal or vice versa, and then you can restate it. And every problem that exists, you should be able to do that because you have the limits of integration, you can figure out the region. So why would I ever need to do this? People ask me. I said, because in reality what happens is somebody's working on a problem, they get a dead end, they don't know where to go, and they may not have actually originated the problem. Or somebody handed it to you, and you're here and you go, I can't do anything, but let me go backwards and see if I can reverse the order, and I may be able to navigate through that problem. Maybe, not always. But your ability to do things like that become essential. So you got this far, but maybe somebody else knows how to finish it. Not this one, I'm just mean any problem. You with me? So do you always have to be able to do every step on your own? Always?
No.
I mean, it'd be really cool if you could. But do you always? I have other instructors sometimes come to me and said, I'm really stuck here. I had one of the professors here, their offspring, I'll be really vague, was going to UCSD and was taking, actually it was this class. And I think it wasn't the final, it was like a practice final. And the student had done it all the way through and got an answer and it was the wrong answer and they were really stressing because they thought they knew what was going on and the answer was incorrect. And the instructor came in and said, what did they do wrong? And I was looking at the problem. I see them, oh, right here. And it was something really, really small and trivial. But I don't remember, they skipped a step. They didn't make an error per se, but there was something, and I said, oh, it's right here. And then I fixed it. And then the answer I got, they said, oh, that was the answer it was supposed to be. But it was one of these things where the student knew what they were doing, but they just couldn't navigate to the end of the problem. So, of course, what are they thinking?
I'm wrong.
They don't have any idea. And it was a really long problem. They were most of the way through it. Let's say 12 steps and it was on step 10. They made an error, but it took them in a completely different direction. But they still understood the big picture, okay? Let's continue on this. Okay. I'm only gonna ask you, for now, I'm only gonna ask you questions you can get. But in case you physically cannot navigate to the end, I would rather you give me that answer and say, I'm demonstrating I know what's going on, I just can't finish it. And it's just not about partial credit. Yes, I would get partial credit. But it's about saying, I understand the big picture. I may not be able to navigate through every single problem. Okay? You engineers, just so you know, a few years ago, I don't remember what year, it was pre-pandemic, there's a class at San Diego State, there's a test. There's 2 tests for engineers. You know what they're called?
EIT and FE.
Fundamentals, and the other one's for professional engineer, usually called the PE. Professional engineer, you've been an engineer for a while, you want to move up, but the fundamentals you take early on. And it was the head of the engineering department, and I think, if I remember correctly, I think it's because their son had been in my class at some point, and their son said, oh, have Mr. Brown do this stuff. So they asked me to teach the fundamentals course, and it wasn't very long, it was like I think I did 2 sessions, and then I did the math stuff, and then somebody else came in and did the chemistry, and then someone else came in and did the physics. Gnarly stuff, it was like 3 or 4 hours. And it was in the evening. That was the toughest part. So there were literally 100 questions. Now, what was cool is I walk in on the first day, and the course is designed, believe it or not, for juniors. I don't know why juniors, I would think seniors, but they said they really want to hit people, it's like end of junior year kind of thing. But I think the course was in January. And they said it's mostly designed for juniors. There were 4 students, and they were all seniors. And everybody else was somebody who had been working in the profession anywhere from 2 to 30 years kind of thing, but had never taken this test, which I'm guessing means they couldn't have moved up the pay scale very far if they hadn't taken this test. There were about 50 people crammed in. They gave them all a set of study questions, like 100 questions. But the 4 students when I walk in were all 4 former MESA students. So the level of relief on their faces right off the bat was, oh, great, you know. And so we got through this, there were about 100 questions. It was calculus, linear algebra, differential equations. That was all it was. And we went through and I walked them through everything. And I let people input. I didn't spend a lot of time because we needed to get through a lot of work. And we went through all the questions, and I saw the questions for the first time after I arrived to the session. Everyone else had them for like a couple weeks when they signed up for the course. So we went through every problem and everything. And then like the head of the program or somebody came up to me and said, how much prep did you do? I said, I didn't do anything. They said, we've been doing this course for years. We've never had an instructor who could even do half the problems. Every problem like that. I said, this is what I do for a living. This wasn't exactly taxing stuff. You know, and I thought, you have somebody who's a professional in my subject who couldn't do them all? That I would think as a student you'd be able to do the vast majority if it's familiar territory. But we got through this, and I thought the most interesting part that I thought was the number of people who were 10 years or more in their profession who hadn't taken this test. Since the test was designed specifically for people at the end of their college career. Now, I also taught the math portion of the GRE for several years, also at San Diego State, different program. San Diego State was just the place where it was offered. It would be 4 Saturdays in a row. 2 of the Saturdays were math, 2 were English, and no particular order. I might do 1 and 3, 2 and 4, 1 and 2, 3 and 4. And then maybe a month later, 2 months later, great program, 40 to 50 students. Now, the GRE it's like the SAT for grad school. And again, this kind of course is typically designed for somebody in their last year of college, because that's usually when you take the GREs. Maybe the second semester of your last year, because you're applying to grad schools. You have to have already taken the test. Everybody takes the math and English, and a lot of people take the subject specific. So if you're an engineer, a computer science in general, you're going to take the upper level one, which is scary. So this course was math and English, and again, it was designed for people in their last year, but when I would teach it, the vast majority were people who were professionals, but now they wanted to go back and get their master's degrees. So there are people that have been out of school for a really long time. So I'm pointing this out because a lot of you are in this position. There are a great many of you who should be taking this GRE in the next year and a half, kind of thing. Because if you're going to go to grad school, now if you're not going to go to grad school, if you're going to work for a while, then go to grad school, no problem. You do lose certain skills, but you'll gain others along the way. Okay, so let's set up one more problem. And where is it? Right here. Okay. All right, right off the bat, this looks terrifying. And I'll just throw an initial condition just for fun.
No, that one's okay.
Let me make sure my eyes are not. X cubed e to the x squared. Yeah, I wrote that correctly. So you're looking at the right side going, oh my gosh. I'll just erase my initial condition. Y of 0 equals -1. Least important part of the problem. Can I just start right now?
Yeah.
Yeah. So what's my mu?
E to the integral, or e to the 2x.
Squared e 2x squared.
Do I like that? I don't know. I don't know if I like that yet.
Let's see.
Yeah, I'm gonna make sure I wrote that down correctly. I don't want this to get harder than. No, I wrote it down correctly. Okay. So now, when I multiply through, I'm now going to have e to the 2x squared dy dx plus 4x e to the 2x squared y. And that's supposed to equal x cubed times what? Rules of exponents.
3x squared?
E to the 3x squared, because
Good.
2x, you.
Because you add exponents to that point. Everybody got it? That one is scary. Why am I less scared by that one?
Because
Because
3
that's
to
a
x
good
squared is
integral.
x cubed, it's a derivative of it.
You can integrate that.
Am I scared by that one? I don't know.
No.
Because that's the derivative of that one. It's not the other way around.
I think we have to use a u sub, like
Wait,
u
but
equals
if-
x squared.
Wait, but if you let u equals x cubed, then you have your.
No, it's going to be a parts.
Yeah, it's a part.
But it's a parts where a derivative
Yeah.
is, the right thing is in the right place.
It's a
Maybe.
good- It's a good part.
I'm less interested in the final, I will walk you through, but I'm less interested in the final answer as I am getting to there, okay? Is it possible when you're working through that you just totally blank out on even the existence of integration by parts? Yeah, but I'm telling you right now, that is the one technique that can show up, and this is why it can show up. Because even though I can find the integrating factor seamlessly, we just did, when I'm multiplying the other side, more often than not, I'm gonna get a product of functions, and I have to integrate this. My life would have been much easier, I make sure I wrote it down correctly. My life would have been much easier if the x cubed were here and the 3x squared were here, do you agree?
Yes.
But that's not the case, and I can't make it be the case. I wish I could, can't. So, if I did it right, this is e to the 2x squared times y. So first derivative of second, boom. Second derivative of first, which is e for, okay, good. So now I can say with certainty, now, here's what I'm gonna do. This is an exam. I'm timed on an exam. I don't have an infinite amount of time. I'm not sure what to do. I got 3 minutes left. I don't know, come up with a situation. Could you do, actually, I'll write it just as a negative x, so it doesn't matter. 2x squared. Could I do this?
Sure.
Now, I did every other problem. I still have a few minutes left. Now I think I'm going to do this one off to the side. Why is it integration by parts? Why is it?
First you can use the U sub, and then you can use the DI method, the integration by parts method.
Well, it's because a product of two things, and it's not a U sub. If it were a U sub, obviously,
Well,
if these guys were reversed, this would just be e to the x cubed and I'd be done, but it isn't. So,
like you have to use both.
both.
Both the parts, like U to make the parts easier to solve, because you could
Yeah.
probably do it by parts, but
So,
that'd be tough.
do I want my u to be the x cubed and that be the dv? Or do I want that to be the u and that to be the dv? Or do I want some weird combination of them? Problem is, I can't make this the dv by itself because I would need a chain rule factor.
Yeah.
Well, U equals x squared is the one you want.
So if I make u equal x squared,
Yeah.
let's off to the side. We did a problem very similar to this today in class today, where we took a problem, we pulled it apart. We did secant cubed, which is so evil. You remember that I called it the Kaiser-Soze problem? It's my favorite. You guys know who Kaiser-Soze is?
Yeah.
He's the most evil person who's ever lived. But people don't know if he's real or not. It's one of the greatest movies ever made, The Usual Suspects. Came out in the late 90s. I've seen that movie so many times, and like I tell people, I'm still surprised by the ending. And he's this mythical character, you find out he's real and who he is like in literally the last 10 seconds of the movie. And my wife swears that she saw that coming the whole time. Oh my God. It's so not true. But it's, Kaiser-Soze was so evil, but people didn't know if he existed. So I always call this, problems the Kaiser-Soze problem. Because his quote, when you don't know he's actually Kaiser-Soze, his quote, greatest quote ever in a movie. He says, the greatest trick the devil ever performed. You know the file? Making people believe he's not real. And this is coming from Kaiser-Soze, who people believed was not real. In other words, Kaiser-Soze was literally the devil. He was so evil. Well, we have Kaiser-Soze problems. This would be one of them. Because it doesn't matter how many things I do correctly, you can't do this in one step. You're gonna have to do this in at least rounds. That's why I'm not worried about your ability to do parts. If you could do this, I'm impressed. But you told us what to do. We're gonna make this x squared times x e to the 3x squared.
Mm-hmm.
Because that now can be integrated. In fact, better, what if I do it like this? Might be easier if I figure it that way. The integral of this is just e to the 3x squared.
Yeah.
So that would be my dv, that would be my u. The problem is the next round might not be clean. Everybody got that? I'm going to do this in rounds. I'm going to say let u equal 1/6 x squared, because I'd rather have the u be the polynomial because it gets smaller. I'm going to call the dv 6x e to the 3x squared dx. Again, this is something you did a while ago. It's really handy if you remember how to do it again. du is 1/3 x dx, and v is simply e to the 3x squared. And here's the key. Will I have a better answer in the next round? So it's uv minus the integral of v du. What do you think? We can do that one. This one ends up being totally clean, doesn't it? So as awful as this was, the hint, or I should say the hint, the observation that if I pull it apart, I can manipulate this. That's a skill that you only get if you're doing problems of this nature. Nobody's going to walk into this one, totally cold, haven't done one in a couple of semesters and just get it. But that's exactly how you do this one. So this is now an easy one, right? I put a 6, a 1, 6, and now I can do that one, and now I can finish the problem. If you can't see it, this one can be done. Not trivial, but we can all do this one. We can do this one. If you don't know where to go, I'm saying you can still go this far. That's my whole point. If you can finish it, hey, more power to you. Should you be laboring over your integration techniques in general? No. Parts will come up.
This weekend, I was just focusing on 15 integrals on flashcards, and then I wrote it out just like that was one of them. Literally that one.
Parts is really the only technique you're going to use for integration. Partial fractions decomposition is going to be a very, very handy technique, but we're not going to use it for integration. We're using it for something else, to break things up, but not necessarily to integrate them, but just to break them up much, much later in the course. And we will review that as a reminder. And you will like it because when it's appropriate to use it, it makes problems a heck of a lot simpler. Okay? So go ahead and press the button. We'll stop.